Many people think that the laws of nature and the universe tell us that everything breaks down. Things fall apart, energy wanes, living things grow old and die. Yes, we have some good laws which explain all that. But what about the emergence of life? What about the complexity of life? Where do they come from? Are these rare, miraculous developments? Or is this kind of complexity inevitable, following natural laws we just haven't figured out yet? Correspondent Carla Wohl went looking for the answer.
It is mysterious how a flock of birds or a school of fish move as one with such grace and coordination, as if there's one brain behind them all, or an invisible force at play. An explanation may be found in emergence, a science that tries to explain complex patterns and behavior that arise in the world around us. Some believe emergence may reveal more than just how birds and fish do this, but how we think and how life itself began in the first place. But while many of science's mysteries long have been explained, gravity we predict with Newton's laws of gravity, and magnetism through Maxwell's laws. Things like this remain largely unpredictable.
Emergence, when you first see it, seems mysterious. But that, if I go back and read the papers at the time of Maxwell, electromagnetism seemed very mysterious too.
Let's start with what we do know about emergence. It's an order we might not expect to see. Usually where there is order, there's a leader, a conductor of an orchestra, or a general with his army.
Orders come from the top and
they go down.
Top-down order, where you have one brain controlling the functions of the entire group.
A leader at the top and many who follow down below. It's just how we expect things to be. So who's in charge here? Him? No. Him?
There's no conductor, there's no general.
There's no leader. There's no director that's telling every fish where to go.
Well, then what about these birds?
There's no one in charge in the birds either.
So if the order isn't coming from the top down, where is it coming from?
The organization comes from the bottom up. So at the bottom we have these things that are following their own sets of rules, often fairly simple. One is to go in the same direction as the other guys. Another is don't get too close, but don't get too far from my neighbors.
And perhaps the most important rule? If someone's coming after you, get out of the way. From these simple rules, very complex patterns can spontaneously emerge.
What we see is a pattern emerging from the bottom up.
And so it came to be called emergent complexity, or simply emergence. Of course, different creatures have different rules, but whether ants, or wildebeest, or this slime mold,
The behavior emerges from the actions that are controlled by the rules. And behavior of the whole is more than the sum of the parts. And that's the flag for emergence.
and you might not have noticed it, but it's not just seen in animals.
Similarly with crowds, there are no leaders within certain types of crowds.
Crowds of people? We do it just like the birds and fish?
Movement is happening at a very much subconscious level. You don't think about how to walk, you just do it.
Keith Still studies the emergent complexity in crowds. He says these people crossing the street have no idea they're part of a larger pattern.
As if they're following each other in long conga lines. What happens is that the first individual that finds a gap is being followed by those people that find it easier to follow something that's moving in roughly the right direction than it is to carve their own path through the crowd.
So emergence happens with all kinds of living things that move in groups.
It can be a crowd, it can be a flock of birds, a school of fish. These are all emergent phenomena when you're getting a large-scale order out of a small-scale interaction.
But emergent complexity can be found in non-living things as well.
Anything I know that exhibits emergence involves a lot of, we might call them agents, a lot of individuals or parts. We could call them parts.
John Holland's first experience with emergence came from some fairly unsophisticated electronic parts that came together to create something almost intelligent. And he saw it a half-century ago with a game of checkers.
You used to look at this as child's play, right?
Yes, I did.
I believe it's your move, too, by the way.
All right.
What changed your mind?
What changed my mind was my encounter at IBM. This was in the early 50s. I was busy at that time simulating neural networks.
Meanwhile, a co-worker, Arthur Samuel, was doing something else.
He programmed the machine to play checkers, and I thought, well, what he's doing is interesting, but that isn't anywhere near as deep as simulating neurons.
It's checkers,
yeah,
right?
It's checkers.
As it turned out, Samuel had achieved something far deeper than anyone at IBM expected.
He programmed the rules, and the machine would move according to the rules.
Not only was the computer following the basic rules of checkers, it had another set of rules as well, a strategy to favor moves that might lead to victory.
Simply by its experience with him and other players, it favored better moves than he did. That machine learned well enough that it could actually beat Samuel himself. With this learning, I have emergence.
It was emergent because when the computer followed simple rules, something as unpredictable and complex as learning emerged. Something until then only living things could do. 50 years later, computers really don't seem to have come all that far.
Good evening, Dave.
How you doing, Hal?
2001 has come and gone.
I've wondered whether you might be having some second thoughts about the mission.
Computers were supposed to be having conversations with us, thinking for themselves. So why can't they? Holland says that's because there's another important factor in emergence to consider. Complexity depends on how connected the parts are to each other.
Compare the central nervous system, our brain, to a computer. There's a major difference. Each element in a computer, each transistor, contacts at most 10 other elements. But in the human brain, each individual neuron contacts 10,000 other neurons.
So the sheer number of neurons in our brain, as well as the number of connections between them, is what makes our brain so much more complex than a computer.
I've got billions of neurons, and each one touching 10,000 others. So we get the emergence, and maybe some of us believe that consciousness is one of the emergent phenomena here.
Consciousness? Could something so complex spontaneously emerge from individual parts following simple rules? It may seem counterintuitive. Many of us think that without a leader or a plan, things become more disordered with time.
Our intuition about the world is that things deteriorate. We get old. We die.
Buildings crumble. We expect decay.
This is the increase that's inevitable in the universe of disorder.
But if order can emerge from disorder, could we actually expect to see something as complex as life itself emerge?
Many of us believe that life follows inevitably as another emergent complex phenomenon.
Bob Hazen, an astrobiologist with the Carnegie Institution, is trying to find out if life on Earth emerged from simple molecules arranging themselves into something living. Hazen hypothesizes that the right molecules under the right conditions will do this, form increasingly more complex structures. And those complex structures will form even more complex structures, and so on, until finally you get life. To start, he needed a simple molecule. He chose pyruvic acid.
Pyruvic acid is a good proxy for the kind of simple molecule that would have been abundant on the early Earth. It's colorless, it's basically odorless. And you load it into a gold tube. It's like threading a needle. You then seal this up.
Hazen is trying to reproduce the energy of the heat and pressure deep within the Earth.
Typical of conditions that might occur in volcanic zones on the floor of the ocean. Seal this up.
He pressurizes and heats the capsules to 250 degrees centigrade.
It's like a pressure cooker. Emergent complexity takes place in any environment where you have lots of agents coming together, molecules coming together, and energy.
And in a week's time, he's recreated the heat and pressure. The one thing missing is water.
And that's the magic trick. Put it in water, and bingo. Those molecules self-organize into an enclosure, cell-like structures called vesicles, a structure which is essential for life.
So here the agents are molecules. The rules are the rules of chemistry. What emerges is one step closer to something biological, an important first step towards life.
And the origin of life must have been a sequence of emergent steps from simplicity to complexity. You go from the simplicity of volcanic gases like carbon dioxide and water to organic molecules.
Still, a vesicle needs to capture energy and nutrients to grow, replicate, and divide before it can truly be a living thing. And whether these steps are emergent is, for Bob Hazen, the great mystery to be solved.
This whole concept of emergent complexity gives us a whole new way of thinking about the universe, going from the simplicity of the earliest universe to the complexity of the modern living world.
Even Hawking says complexity is the study of the 21st century. Maybe in 20 years, it'll be the standard science for all I know.
Scientists would love to quantify emergent complexity. We'd love to be able to have a formula that told us what systems become complex, how complex they become.
My guess is that we will find some laws that will let us describe some things in these complex adaptive systems, patterns that we can recognize and maybe even make predictions about. And that's the great advantage of Newton, of Maxwell, and maybe someday we'll get our own Maxwell.
Was that voice in the wilderness?